Swayam Prabha. Digital India. Educated India.
Now, one more example, that the determinant of 2 cross 2 matrices is a number is what the determinant of A, B, C, D, you take it, then cross multiply AD, cross multiply BC. So, this is called as determinant of 2 cross 2 matrix. Now, the determinant of 2 cross 2 matrix is denoted by GL of 2 comma R. It is the rectangular matrix A comma B comma C comma D is rows and columns, where A, B, C, D belongs to real number, and conditionally the determinant should not be equal to 0, mean it is a non-singular of 2 cross 2 matrix. Non-singular mean the determinant not equal to 0 is non-singular. If equal to 0, then it is a singular matrix. Therefore, it is a 2 cross 2 matrices with real entries, and non-zero determinant is a non-abelian group under the operation. So, it does not satisfy the abelian group, therefore, it is a non-abelian, but it satisfies the group property. Therefore, you product the two matrices, and then we have what first row into first column is this entry, first row into second column is this entry, first row into first column is third entry, first row into second column is fourth entry. So, that this is a matrix multiplication of two matrices. Now, we have another example. The set of all 2 cross 2 matrices with real entries is not a group under operation defined in example, because inverse do not exist when the determinant is 0. So, make a note of this, most important, that see the previous example is not abelian, and these entries are real, therefore, it is not a group. And then because the operation defined in example 9 does not exist when the determinant is 0. So, if determinant is not equal to 0 only, it exists. So, previous example, that abelian is say you take 1, 2, 3, 4, and then 1, 3, 2, 2 or 2, 2, 5, like that you take it. So, you multiply them, 1 into 1 is 1, 2 into 2 is 4, 1 plus 4, 1 into 1 is 1, 2 into 2 is 4, and then 1 into 3 plus 2 into 5 is 10, then 3 into 1 is 3, plus 4 into 2 is 8, and then 3 into 3 is 9, and then 20, then we have 5, 13, and then 11, and then 29. Now, you multiply in other way, right, that is AB. Now, BA you do that, you find out the value. So, 1 into 1 is 1, and 3 into 3 is 9, and 1 into 2 is 2, plus 3 into 4 is 12, and then 2 into 1 is 2, plus 5 into 3 is 15, and then 2 into 2 is 4, plus 5 into 2 is 20. You see, it becomes 10 and 14, 17 and 24. Therefore, these two are not equal. Therefore, A star of B equal to not equal to B star of A. Therefore, previous example is not abelian. So, keep it in mind this, that is why we come across the example 10, right. So, example 10 says that 2 cross 2 matrices with the real numbers entries is not a group under the operation defined in example 9, because inverse do not exist when the determinant is 0, right. Next we have a summary of the group, and F can be of any rational or real or complex or integer modulo P, and the matrices L is a reflection. So, these are all the standard notation of set theory. Now, you can understand easily that you take a set which are all the sets or groups, and what is the meaning of corresponding set notation, and what are all the identity element, and what are all the inverse element, whether it is abelian or not. These are all the question rises in your mind, and then this is the table of so far we discussed the example, and you can easily understand, right. So, how to do that? That is, you start with Z. Z is a set of all integer. You take the operation is addition, and if you take addition operation, the identity is 0, and then it form of element is a k, and then if you take element as a k, then definitely minus k is inverse of that k, and it obeys the abelian property that a plus b equal to b plus a. And for q plus means it is a rational numbers with addition operation, that is q plus of only positive numbers of the rational p by q, and you have to take the operation as a multiplication, and then the identity is 1, and then m by n is a formation of an element, and then it inverse is n by m, therefore, it obeys the abelian group. Abelian as well as it satisfies the group property, therefore, it is a abelian group. Next, integer modulo n mean start from 0, 1, 2, 3 and so on, n minus 1, that is called it as addition modulo n. Multiplication modulo means 0 is omitted, addition modulo is 0 is included, therefore, 0 acts as identity, and the formation of the number is a k, and then it becomes, so if n comes then divided by n it becomes 0, therefore, n minus k is the inverse, and then definitely it follows what abelian, therefore, it obeys all the 4 properties of the group, therefore, it is a abelian group. Next one is R star. R star is a real number. A real number is a multiplication. Under multiplication operation you do that, and except 0, right, it has identity 1, and the formation is x, x is a real, then 1 by x is also real, and it obeys the commutative property or abelian, then it is said to be abelian group. Next one is GL of 2 comma f mean the matrix. The matrix is 2 cross 2, and then the element may be rational or real or complex or whatever may be the set system. Now, under matrix multiplication you do that, so that the identity matrix is 1 0 0 1, and then the formation of the elements is matrix notation, first row first column, first row second column, second row second column, third row third column, and then the inverse A inverse is change the place of diagonal, and then opposite diagonal also change place and change in sign, and find the determinant. So, this is determinant of the given matrix A, so that AD minus BC should not be equal to 0. So, that A inverse, this is the inverse which is equal to D by AD minus BC minus B by AD minus BC minus C by AD minus BC and A by AD minus BC. Find the inverse of A and check it out whether it is a group or not. It obeys, whereas it does not obey abelian group, because A star of B equal to not equal to B star of A. So, this condition is true if the determinant not equal to 0, right. So, the determinant of A is equal to this is not equal to 0. Now, for UN, UN is a multiplication modulo n, right, and then except 0 everything is okay, then it is identity having 1, the structure is K, and under integer modulo we studied in unit 2, check it out that the linear Diophantine equations of the modulo n of kx under modulo n is 1 and it obeys the abelian. Then R power n is a real number of n tuple, and the component wise that it is addition, and then a n tuple we can return like this 0 0 0, and then n tuple ordered or pair is a1 a2 and so on an, and corresponding values is negative minus a1 and so on minus an. So, if you apply the abelian type, that A star of B equal to B star of A, then it obeys the abelian group, therefore, it is a abelian and abelian group. Next, SL of 2 comma F stands for the matrix for multiplication, and then it obeys the matrix structures of identity is 1 0 0 1, and the structure of the matrix is A B C D, and take the diagonal or take the determinant of this matrix AD minus BC equal to 1, and opposite diagonal you do that, so that you have a inverse of the matrix, and surely it does not obey the commutative property or abelian property. Hence, it is not a abelian group, and if the condition AD minus BC equal to 1 and it obeys the group structures. So, this is the general idea about SL of 2 comma F. Next one is DN. DN stands for dihedral of the composition, and reflect the 0 as identity because it lies in the same plane, and R alpha comma L is a corresponding form of the element, rotational basis of 0, 30, 45 and then 60, 90, 180, 270, 360 and so on. We have to do that, so that the rotation ideas it will come, whereas it does not obey A star of B equal to B star of A, because anti-clockwise direction comes, it is become negative. Therefore, it does not have abelian group structures, implies it is not a abelian, whereas it obeys the group properties. So like that you have to check it out if you have a set, or if you have a formation of the set like that from the number system or a generalized structure of assumption of your operation, and check it out whether it is a group or not, whether it is a semi group or not, whether it is a monoid or not, whether it is a group or not, or abelian group or not, or subgroup or not. These are all the plenty of things you can imagine, or you can think on your own way, and mentally you can check it out these laws, axioms of groups, so that the formation of the set can easily design. Now, keep it in mind this let us go some properties of group theory. So, first one is uniqueness of the identity. In a group there is only one identity element, right. So, you take whatever may be the set group, surely it has only one identity element, then only it obeys all the properties of what group theory. So, it is very important that check it out whether it is a uniqueness or not. Suppose the set having two identities, say E and E dash of G, what happened? AE equal to A will come for all A in G, and E dash into A equal to A for all A in G will come. So, we choose that A equal to E dash in 1, A equal to E in 2, it yields E dash into E is E dash will come. Obviously, E dash say and E dash into E equal to E will come. So, from this both E and E dash are equal to E dash E. So, they are equal to each other, then the cancel it only E will come. So, this way we can write what uniqueness of identity. Next, we have to follow the cancellation law of the group. So, in cancellation law of the group, in a group G, the right and the left cancellation law hold that BC equal to CA implies B equal to C, and AB equal to AC implies B equal to C. So, we are going to give the proof of this. Suppose BA equal to CA. So, in a group every element having the inverse. So, let A inverse be the inverse of A, and what you have to do? You have to multiply right by A dash. So, this yield BA into A dash equal to CA into A dash. Since it follows the associative property, therefore, we can write this expression as B into AA dash equal to C into AA dash. Now, you see that AA dash is E, this is E, and this is also E, therefore, B equal to CE, and then we have to cancel it this and this. So, B equal to C, because he is having the inverse, since E is in G, therefore, it has an inverse, we can easily cancel it. One can prove that AB equal to AC, it means the same way we have to try with post to multiply by A inverse, and then B equal to C will come, that is AB equal to AC, and A inverse of AB equal to A inverse of AC. So, A inverse of A into B equal to A inverse of A into C. So, we have E into B equal to E into C, therefore, B equal to C will come. So, multiplying by A dash on the left, so that we can get what? The cancellation property of this group. Next, uniqueness of inverse. So, already we come across uniqueness of identity. Now, we are going to see uniqueness of inverses. For each element A in group G, there is a unique element B in G such that AB equal to BA equal to E, right. So, suppose B and C are both inverses of A, it means AB equal to E and AC equal to E. Now, AB equal to, so instead of you call this as 2, this as 1, and substitute the values of E equal to AC. Now, with the help of the cancellation law and B equal to C, therefore, we got the desired answer of what? Uniqueness of inverse, right. Next, we have the Sock-Shoes property. It means for group elements A and B, AB whole inverse is equal to B inverse into A inverse. So, we have to prove the statement. So, what you have to do, multiply the one element to the inverse of the another element. So, AB is one element, mean AB whole inverse exists because it belongs to the group. Now, inverse property, it becomes E according to the statement of what AB into this becomes B inverse A inverse. So, you take what LHS. So, associative property, this becomes like this. So, it becomes E, therefore, A into E into A inverse, which is equal to E. So, E is proved. So, this way we can write what the proof of AB the whole inverse equal to B inverse into A inverse. So, we have a previous theorem that AB whole inverse equal to B inverse A inverse. Now, we have a table of multiplicative group and additive group. If A dot B or AB, you can do that, then it is called as a multiplication. For addition, A plus B, we can denote like this. For multiplicative group, we have identity is either E or 1, whereas for additive group, we have the identity is 0. For multiplicative group, inverse is A inverse, and for additive group, we have a inverse is minus A. And for a multiplicative group, we have A power n, and for additive group, we have NA. And then for multiplicative group, we have AB inverse, whereas additive group, we have A minus B. Now, we have to recollect, if G is a group, then the identity element of G is unique. For every A in G has a unique inverse in G, then for every A in G, A inverse the whole inverse is A, and for all A comma B in G, A dot B the whole inverse equal to B inverse dot A inverse. So, these things recollect it, so that later stage we can use it, how it works. Now, we have a lemma given A comma B in the group G, then the equation A dot x equal to B and y dot A equal to B, then we have a unique solution for x comma y in G. With the help of the two cancellation law, you have A dot u equal to A dot w, which implies A u equal to w, and u dot A equal to w dot A implies u equal to w. This holds in G. Now, we are going to discuss a subgroup. So, already we discussed the from the group, the first property in a group, it has a 4 property, right, closure property, associative, existence of inverse, and then existence of inverse, existence of identity, associative, and closed. For the 4 properties, the first property and fourth property satisfies, then it is said to be subgroup, or we can write in other way, a non-empty, say you set G is equal to 1 minus 1 I minus I, you take it. So, H is a subgroup of 1 comma minus 1 under star multiplication, right. So, G and then H is a subset, and then it has this and this has this. So, check it out whether it satisfies the first property and fourth property, that is, say if you have a star 1 minus 1, if you have 1 minus 1, 1 into 1 1, and it is minus 1 and then plus 1, you see existence of identity having, inverse having, closure property having. So, similarly it is holds good for the Cayley table of the quadradian 4 group of star 1 minus 1 I minus I, and then we have what minus 1 I minus I plus I plus I and minus I. Now we have a Cayley table of 1 minus 1 I minus I minus 1 plus 1 and then minus I plus I and then I minus I and then I square is minus 1, I into I square minus 1 plus 1 and then minus I and then plus I and then I square minus 1 plus I plus 1, and here I square minus 1 minus plus minus 1. So, you see it is also forms a group, but it is a G, it is a H, and H also satisfy the properties of group. Therefore, H is a group of G is said to be subgroup under the product in G. H itself form a group. So, it is also forming a group. So, like that we can define a subgroup. So, it is a subset, also it is subgroup because it satisfies the subgroup properties. Now, we have a lemma, a non-empty subset H of a group G is a group of G, subgroup of G. Non-empty subset H of the group G is a subgroup of G if and only if A comma B in H implies A star of B in H, A in H implies A inverse in H, implies it is closed and inverse, because if inverse property satisfy, ultimately it has a identity element comes, because A star of A inverse equal to E, which is equal to A inverse star of A. So, it satisfies the inverse property. Therefore, it follows the group structures. So, we can easily prove that it satisfies the group as well as subgroup. Now, keep it in mind this, we have a proof that H is a subgroup of G, then it is obvious that the properties 1 and 2 must hold. Suppose conversely that H is a subset of G for which 1 and 2 hold. So, in order to establish that H is a subgroup, so that all that is needed is to verify that E in H, that is associative law, holds for the elements of H. Since the associative law does not hold for G, therefore, it holds for all more, so for H, therefore, which is a subset of G. So, if A in H, the part 2 of that statement is A inverse in H. So, by the part 1, E is equal to A inverse in H, therefore, it satisfies the inverse property, implies A in H implies A inverse in H. Then we have a lemma, H is a non-empty finite subset of a group G, and H is closed under multiplication, then H is a subgroup of G. So, it means number of element in that set is finite, mean the elements are finite. Suppose you take a G as a quadradian 4 group, right, there 1 minus 1 I minus I, and H is a 1 comma minus 1. You see number of element is 4. So, number of element in H is equal to 4, 2, therefore, it is a finite. So, if H is a finite, H is a subset of G and then it is a finite. So, it is closed, therefore, H is a subgroup of G. So, obviously, it obeys. Now we have a proof to show that whenever A in H, then A inverse in H. Suppose that A in H, that A square equal to A into A in H. Similarly, A cube can be written as A square into A in H, and we can extend it to any power of A, therefore, A power m in H implies H is closed. So, infinite collection of elements of the number A square and so on A power m must all fit into H. So, which is finite subset of G. Thus, there must be a repetition in the collection of elements, that is for some integer R H with R greater than S greater than 0 for A power R equal to A power S. By the cancellation law in G, A power R minus S equal to E. So, when C is in H, since R minus S minus 1 is positive, therefore, A power R minus S minus 1 belongs to H, and A inverse in A power R minus S minus 1. Therefore, if you multiply them A into A power R minus S minus 1, it becomes base or equal power add, therefore, it becomes A power R minus S equal to E, implies A inverse in S H, which is completing the proof of the given lemma. So, this way we can prove if H is a finite and it is a subset of G, and obviously H is a subgroup of G according to the proof of the theorem. Next example, let G be a group of non-zero real numbers under multiplication, and let H be the subset of a positive rational numbers, then H is a subgroup of G. So, and G is a real number, real numbers, and rational is a subset of R. Obviously, it is a subgroup of G. Already we discussed the number system, and we can easily check that the rational number is a subgroup of G, because G is a group. Obviously, H is a subset, and also it has a positive, and it has an inverse, and then closure property. Therefore, H is a subgroup of G. Another example, let G be a group of all real numbers under addition, and H be the set of all integers, then H is a subgroup of G. For example, let G be a group of real numbers of the matrices A, B, C, D with the determinant of the 2 cross 2 matrix is AD minus BC not equal to 0. Now, under multiplication, let H is equal to matrix you coin A, B, 0, D, which belongs to G such that AD not equal to 0. Now, you see that G is a group and H obeys the properties of closure as well as inverse. This implies it is easily verified that H is a subgroup of G, because we have the inverse of the matrix exist. Obviously, A star of A inverse belongs to E, which is exist. Next example, you take a complex number and see complex number is C, which is set of all ordered pairs A plus IB such that A comma B belongs to real, and then A plus IB into A plus, that is root of A plus B, in the sense that A square plus B square which is equal to 1 we have to define. So, you can check it out. A and B are real but not both 0. So, we have to consider 1 plus 0 I is identity, right, and then we can easily find the inverse under multiplication. So, we have to check here Z equal to or G is equal to A plus IB, which is a complex form. Then I say if you have a closure that is A star of B, which is equal to A plus IB into C plus ID, we have to take it. So, what you have to do? Multiply them AC, multiply them minus BD plus I into BC plus AD will come. So, this way we have to do the complex multiplication. Similarly, you check it out, A star of B star of C, which is equal to A star of B, that is A star of B star of C. You may check it out the same way of 3 numbers, and for the inverse we have to take 1 plus 0 I. Sorry, identity we have to take, for identity you have to take E equal to 1 plus 0 I. For inverse A equal to A plus IB, then A inverse equal to 1 by A plus IB, which is equal to take a conjugate A minus IB by A plus IB into A minus IB, which is equal to A minus IB by, so this becomes A square plus B square, this becomes A square plus B square, because A minus B into A plus B is A square plus B square, because I into I square minus 1, therefore, it becomes A square plus B square, therefore, A by A square plus B square minus I into B by A square plus B square. So, corresponding inverse can get it, and we have a subgroup H A plus IB, a structure like that, definitely it satisfies the first property and fourth property, therefore, it follows the subgroup. Now, we have a definition, let G be a group and H is a subgroup of G. For all A comma B in G, we say that A is congruent to B under modulo H, implies that A is identically equal to B under modulo H, or rather we can say that A into B inverse also belongs to H. So, already we come across in the number theory of congruences, x y is identically equal to 1 under modulo n, the same structure if we can write in terms of the subgroup as A into B inverse in H. So, we have the relation A is identically equal to B under modulo H is an equivalence relation. Equivalence means it is a reflexive, that is the set is a reflexive and the set satisfies the symmetry and set satisfies the transitivity. So, we have a relation. So, A is identically equal to A under modulo H for all A comma B comma C belongs to H. A is identically equal to B under modulo H implies B is identically equal to A under modulo H, and A is identically equal to B under modulo H, and B is identically equal to C under modulo H implies A is identically equal to C under modulo H. So, to show that the first part A is identically equal to A under modulo H, we must prove using the definition of congruences that A inverse in H, that which is equal to E, obviously E in H, therefore, H is a subgroup of G since, therefore, A inverse equal to E and A inverse in H, which implies the first part is proved. For second part, suppose A is identically equal to B under modulo H, that is, suppose AB inverse in H, we want to get from this B is identically equal to A under modulo H, or Equivalently, BA inverse in H, since AB inverse in H means the subgroup AB inverse the fold inverse in H. So, by Lemma, by previous Lemma says that AB fold inverse, the fold inverse is equal to B inverse the whole inverse into A inverse, therefore BA inverse. So, BA inverse in H, therefore B is identically equal to A under modulo H. Finally, we require that A is identically equal to B under modulo H and B is identically equal to C under modulo H. The forces that A is identically equal to C under modulo H. Therefore, the first congruence translates into AB inverse in H, the second into BC inverse in H. Now, H is a subgroup of G, therefore, AB inverse into BC inverse in H. However, AC inverse equal to A into E into C inverse, which is equal to A into B inverse B into C inverse, which is equal to AB inverse into BC inverse. Hence, AC inverse in H, this forms A is identically equal to C under modulo H.